Pleasure to have Godwin with us with ICTS and let him talk about exterior field theory for Hawking radiation.
Thank you all for being here, and thanks to Arnav for inviting me. Coming to ISC is always a pleasure, and it's been a while since I've come, and it's still as green and as nice as I imagine it to be. Okay, so I will talk about some work that I have been doing with, I have done with Loganayagam at ICTS, which is in this paper. And a follow-up work with a student who's graduating this year, Shiva. So this is so roughly I will be talking about this question of an exterior field theory for Hawking radiation. I will explain each word in that title as I go on, but the question is centered on black holes. So let me maybe write this with it's a lucky coincidence. So the question is about a black hole, and we all know about black holes since Einstein's theory of gravity as an object which has a surface called an event horizon, which not even light can escape, right? So we know these objects called black holes, but then around 50 years ago, since Hawking, we also know that black holes radiate. They radiate, in fact, like a hot metal ball kept outside, right? And for a Schwarzschild black hole in flat space-time, for example, we know that the Hawking temperature of the black hole goes inversely as the mass of the black hole. And if you want to restore units, you put a kV there. You make this a radius and put an h bar c over there. And you see that there is an h bar on top, and so it's quantum suppressed. And you would say it's a very, very small temperature. But nonetheless, it's finite and non-zero, right? So we know that classically, if you throw something into a black hole, it'll get sucked in, okay? But then now we know that if you account for quantum fluctuations from Hawking, we know that black holes in fact radiate, so they actually throw stuff out. So if you now say you live in a QED world and you threw in an electron, it can scatter against a Hawking photon, which can undergo many, many scattering processes. Let's say another Hawking photon becomes a Hawking electron, Hawking positron, scatters, photon, and then maybe comes out as something. Okay, so say your detector is here, say your emitter is here, and your detector is there. The question I'll be trying to ask is, how do you understand such process? Okay, so this will be the basic question I'll try to ask and give you an answer in a very, very clean setup, very, very simple setup, as you will see. But this is the broad question that I want to answer. Yeah. It can emit whatever you want. So I'm just sitting outside a black hole, throwing stuff into the black hole, and I want to understand. I want to set up a field theoretic picture for how to understand fields falling into the black hole, for example, and scattering against the black hole. Okay. So let me start with the first question. Can you set up a picture like this? Okay. So the question that I will really be trying to ask and give you an answer for is, can we set up the above picture? Not what the picture means, because I have to give you propagators, vertices, and to do usual Feynman diagrammatics, to do usual QFT calculations outside a black hole, right? Which has to account for the effects of the black hole in the sense that there should be propagators which will just fall into the black hole, as well as receive Hawking fluctuations from the black hole. Okay. Okay, great. So basically what I want to set up is an EFT, an exterior field theory. Okay, and that's what I mean by an exterior field theory. A field theory which is purely in the exterior of the black hole, whose vertices and propagators are given, and you integrate the vertices from the black hole horizon all the way until infinity of the space. Great. So what do we want this exterior field theory to do? Because I haven't yet told you what you're really computing. Right? In a usual QFT setting, it's very clear you're computing correlation functions and then LSE into S matrix. Okay, at the moment I'm talking about it very generally because we want to answer this question eventually for real black holes out there. But I will settle comfortably to ADS, and I'll tell you why. Yeah, so an exterior field theory. But what kind of exterior field theory? What do you mean by this? What do we mean? And what should this exterior field theory do? let me call this an EFT for short, not a capital EFT. First of all, it should account for dissipation, which is falling into the black hole, as well as the fluctuations from the black hole. The quantum fluctuations of the black hole, which are the Hawking radiation. Yeah. And as such an exterior field theory, if you write down the propagators and vertices, you would expect that it should depend on the charges of the black hole. So, for example, on the mass and other charges. For example, if you just have a massive black hole, no charges, no other charges, you'd expect that it should depend on the temperature, right? So temperature and other chemical potential. Right? And what should it compute? Remember that we are in a gravitational setting. We have a black hole in between, so you can't do something like an S matrix. You can do a generalized form of an S matrix, where you have to put the black hole into the in state and the out state. More complicated, but one thing that you can compute is a gauge invariant. What is the only gauge invariant observable? Those are boundary correlators, and those are the only things you can compute. And then the question is, can you do an LSE kind of thing? Is there an S matrix kind of setup that you can eventually set up? I will not answer that question today. We can talk about it. But what I will compute is gauge invariant observables which are boundary correlators. Exactly. But when you think of an S matrix, you think of a unitary object, right, which takes in states to out states. Now, if you don't put the black hole in the in state and out state, the in state could be 5 particles, the out state could be none, right, because all of it would feed into could go into the black hole and be lost.
I mean, I assume that wait for long enough for the black hole to evaporate.
Yeah, so then you would have to put the black hole into the out state. Oh no, we're not waiting. No, we're not waiting. We're not waiting for the black hole to evaporate. This is yeah, this is catching in a black hole. Okay. Yeah, thanks. Should compute. Okay. Okay. So the question is now clear. What we have to do. Yeah. Yes. Yes. Yes, you would have to do that, but I'll not do that today. So what I will do, okay, it'll be clear what I will do. I will compute these correlators and I'll show you a story for these correlators. To get an S matrix like observable for them, which will be these generalized S matrix kind of observable that Karen Hort and others have been talking about, that is something that we've been thinking about and we don't have a clear answer for it. So I'll be computing these and leaving it there for you.
I mean, the boundary correlators and principles would be
yeah, that's true. That's true. But this is a question you could ask in flat space quantum field theory as well, right? Yeah, but then if you compute a boundary correlator, you can always do an LSE on it. And sorry, if you compute a correlator, you can always do an LSE on it and get. That is indeed possible. Yeah. Sure. This is a fair criticism. I don't have a great answer to it. Yeah. Question is what effective field theory will you write down? Right. Let's say you forget about the black hole and you just want to put phi cube theory in the exterior. You just use usual propagator for the phi cube theory, and you say usual vertices, and you integrate in the exterior of the black hole with the black hole spacetime, curved spacetime QFT. Question is what boundary conditions will you put on the horizon? Because the horizon is a new boundary that you have included. What boundary conditions will you put? I give you an answer. Yeah. Yeah, so those are ingoing boundary conditions, which is one prescription people do. People just do thermal field theory on the exterior, put an ingoing boundary condition on the horizon, which is that everything just falls in. But if you're outside, you just see thermal field theory because the black hole is hot. But that is exactly one level below the question that I'm asking, because I'm asking what do these kind of processes look like? A Hawking photon came out of the black hole, and you want to account for that effect, right? Because falling into the black hole is a classical calculation that you can set up. Indeed, question is how do you account for the Hawking physics of the black hole? Okay, great. Thanks for that. I will remember that. Yeah, so now question is what kind of boundary correlator should you compute? Because should you just compute if you were a quantum field theory student from a quantum field theory course, you would just say, oh well, compute time order correlators and you'll be done because you can do an asymmetric vector. But that's not quite true for a system which has fluctuations and dissipations, because this is something that we have learned from the founders of quantum field theory, including Stringer, the 60s, Stringer and Feynman, Godwin, Keldish. We've learned from from them that if you have systems where there are these fluctuation and dissipation physics happening, the correlators that one should compute and the correlators one should try to understand are a more general set of correlators called Schwinger-Keldysh correlators, which are correlators which have a time ordering as well as an anti-time ordering. Okay, so let's say so this will be my time ordering symbol. This will be my anti-time. Okay, so to those of you for whom this doesn't look familiar, just think of this as like when you want to study an open system, you never do states, you always do density matrices. The density matrices are what you call states, and the density matrix always has a bra and a ket, right? The bra backward evolves while the ket forward evolves, right? It gets an e to the iht, e to the minus iht. So you should always forward evolve and backward evolve, which if you want to do the pathological kind of way, you will just say, oh, forward evolution will just give you time order operators, backward evolution will give you anti-time order operators. The most general thing is this. So that's the story. So the question is now clear. What the aim is now clear. We want to set up an EFT. So set up an exterior field theory which computes boundary. Okay, so for the rest of the talk, I'll just be focusing on this, and I basically will not say this again and again, but this is what we want to compute. Okay, now I start apologizing. I will tell you that I don't know how to do this for a flat space black hole. Okay, but I do know how to do this for an ADS black hole. Okay, and the hope is that I can do this ADS computation and eventually take an LADS going to infinity limit in a well-defined manner. This is something that we've been working on, and we have some results, but we don't have anything concrete to say, so I will not tell you that story. But even ignoring that as well, within ADS itself, you learn some very qualitative lessons which we think will just go to flat space. Which you can just take the results and try to do the flat space question with that asymptotically flat space question. No, I will not use the dual CFT, but there will be CFT intuition going into how to do this calculation. I'll tell you in a minute why this calculation is difficult. Yeah, yes, yeah. I'll do this for ADS d plus 1, d greater than 2, greater than or equal to 2, including BTC. We will not be seeing any of the IR effects. Okay, so we'll do this for ADS d plus 1 cross shield. Okay, so you can already see that I should really apologize a lot because I'm going into a very simple setup. I'm not even doing black hole because you might think that a lot of physics about this question it has to do with the fact that it's a black hole, it's a spherical horizon. But to start with, I don't want to deal with spherical harmonics and vector spherical harmonics and all that blah. I want to do a very simple computation with just plain waves, so I'll do black brane. Okay, generalizing this to a black hole is not very difficult. This is something I've done, and this is not in the papers, but it's not very difficult. Okay, so because it's an open system. Yeah, you have to account for the dissipative as well as the fluctuative effects, and that you can only do in a Schwinger-Keldysh formula. Okay, great. So let me come to how do you do this. Come to how to do this for an ADS-D plus 1 Schwarzschild black brane. So by ADS-D plus 1 Schwarzschild black brane, I mean this solution of the Einstein equations. So I'm writing it in ingoing Eddington-Finkelstein because I find the ingoing Eddington-Finkelstein convenient to use. So this is the d-1 dimensional plane. The B is the ingoing Eddington-Finkelstein. And f of r is the M-blocking factor. This is the horizon. Okay, that's what I mean by ADS-D plus 1 Schwarzschild black brane. It's just almost Schwarzschild kind of thing. It's basically what you will write down in flat space except for this f of r. Okay, so the temperature of this black hole, let me write it down just to define this symbol. If you do, you can derive the temperature for this black hole from black hole thermodynamics, or if you do a Euclidean complexification trick. So the beta Hawking is 4 pi by d RH. Another thing I'm working in, I'll work mostly in LADS equal to 1 unit. So I just here I'm giving you the LADS because otherwise it looks very dimensionally wrong. I'll work henceforth in LADS equal to 1. So okay. So with that quick thing about what the ADS black hole I'll be working with is, let me ask the general question: how do you compute Schwinger-Keldysh correlators in a particle set? Okay. Okay. So if you were doing a usual path integral for quantum field theory, let's say in the quantum field theory 1 course, you would say, okay, let me draw a time plane, imaginary time, real time, and then do a path integral along this contour. Right? I'm not drawing a straight line because, well, you think that it's just the real time line, but then you have an I epsilon prescription to make the path integral well defined, and you'll just do this contour. Right? And if you want time. Real time. Okay. But then if you really wanted anti-time ordered correlators, you would just say, oh, put the opposite minus I epsilon prescription, and you would get this. Okay. To do the most general set of correlators, just do the full thing. Okay. Now, most people usually rotate this diagram because one usually wants real time going upwards, because time usually goes upward. So let me draw that diagram like that. This is just that. Okay. And since you're computing this Schwinger-Keldysh correlator in a thermal state for the boundary, because you have a black hole in the bulk, you have a Euclidean evolution, imaginary time evolution by length beta, and this is really a circle in imaginary time, right? I can't really draw that there. I can't neither draw it here, but I'll draw a chimera kind of diagram, part Lorentzian, part Euclidean, where you have the Euclidean circle to start with, and then you're doing a genuine Lorentzian evolution forward and then backward. Okay. So I have some color chalk. This is the Euclidean time circle. This is Lorentzian evolution. Okay. Okay, so this is the path integral contour you want to work on the boundary, and you want to compute correlators which are in general on this path integral contour. So let me give you an example for that as well. If you put just 3 operators here, you will get basically 3 operators on this line which are just time ordered correlators. If you solely put it here, you'll get anti-time ordered correlators. If you put a general set of insertions on this full contour, you'll get that. Okay. Okay, now the question is, what is the bulk extension of this? Because you want to do a bulk computation to get these objects. Because remember that our motivation is completely in the bulk. We are computing these because these are gauge invariant observables. So Schwinger-Keldysh contour on the boundary, but then what is the bulk extension of this is the question. Let's go slow. You know that, well, the bulk extension of the Euclidean time circle is just a cigar. Now, the non-trivial part of this is what is the bulk extension of that, and that answer is what we call the GRSK. This whole contour, this whole thing, is what one calls GRSK, or gravitational Schwinger-Keldysh. Yeah. So there are 2 copies. So basically, what I'm trying to say is that let me draw a line on this so that it's clear. There are 2 copies. So if you go here, you can cross through the boundary, then you come back there on the other side. Okay. So it's a Euclidean cigar, and then you put your finger in it. Okay. So this is a pictorial representation of the GRSK. Now let me write down some equations. You can add gravitons to the picture. I will work with scalar theory. I'll tell you what. I haven't specified the theory that I'm working in, so I'll tell you the theory, but you can do graviton. Yeah, fair.
Quantum part is putting in some
Yeah. So this is kind of the yeah. I'm not making any big claim about understanding the full quantum gravity of this question or anything. This is just this question, very simple. Okay, so generally the question would be to ask, this exchanging particle can be anything, right? Everything in the Standard Model plus gravity. But then you don't want to start with doing like, say, gluon.
Gravitons will
always be there. So will photons.
So, but the graviton effect will be the leading one, because suppose you did quantum mechanical science, you're putting in a particle in some, and you calculate the potential, gravitational potential. There's going to be some deflection of that particle.
Yeah, because of the potential, indeed.
That in the quantum physics language is going to be given by
With, yeah.
infinite lattice.
Yeah. Fair. Is a graviton. Yeah, I agree. Okay. So you have to do a graviton computation, but you see the graviton computation eventually also you can write it as a couple of scalars with a particular coupling. Okay. So you want to start by understanding a scalar theory and then do gravity. Is that a fair answer? Okay. Okay, so let me put a few equations into those words I said. So basically, what do we want? You want a doubled geometry, okay, over which you can do a computation. This double geometry must have two boundaries, okay, and that double geometry is easy to specify. You just take the Schwarzschild-Blackburn metric that I've written down there. Let me write it down again. And you complexify the r coordinate. Okay, so let's go to the r. Note that this plane is different from that plane. Be very careful of this. Real r. Usually you do a let me call this RH. Usually you're just doing a computation over this real line. Okay, but what I want is two copies of this, so I just take two copies. Okay, but then you need some specification of this, so the specification is as follows. Let me define a mock tortoise coordinate, basically a tortoise coordinate, as follows. That the beta is the Hawking temperature of the black hole that I put there. Okay, so this is the usual tortoise coordinate construction. This tortoise coordinate has a logarithmic branch cut starting from RH, which you can draw along the real axis. Okay. It's clear why it has a logarithmic branch cut, because it has a 1 minus RH to the d by r to the d, so it's like an integral over many poles accumulation in the real line. So there is a branch cut along the real line. So I just choose this contour as the geometry. So this is a non-trivial prescription, hasn't been proven yet. But it has been tested by many people across over the last 7 years, since 2018. So this prescription, the GRSK prescription, due to many people, I'm mentioning a few of the major works, and finally this thing was pinned down at the end of the day by this paper by Liu and others. In 2018. So since 2018, this has been checked for many situations, including charged black holes and rotating black holes, and theories in many of these situations where it's clear that unitarity works, causality works, thermality works, and many of these consistency checks has been done again and again and again, and it just works. Okay, so remember that we're very far away from the picture I initially wrote down. The picture I initially wrote down was an exterior field theory purely in the exterior of just one copy of the black hole spacetime, right? You want to write down Feynman vertices, propagators in the exterior of one black hole. But then this sounds like, oh, you have to take two copies and then do this computation. Okay, so this is one of the major punchlines of this talk, that if you start doing this computation on this geometry, okay, eventually you write down answers for correlation function, generating functions on this geometry. Okay, after all the calculation of dust settles and you do this monodromy integral in some very complicated way, at the end of the day you get some exterior field theory. Okay, so that's the punchline. So let me put a few words into how this computation goes. Let's consider. This is just the definition of a mock tortoise coordinate, zeta, and this zeta has a branch cut here, branch point here. Zeta and this cut. Okay, so let's consider for simplicity phi cubed. This you can do for any phi to the n is what we have shown, and there are some. Yeah, so to draw that here, you can. So you have 2 points on the boundary. Those are those 2 points, and then you go into the bulk, cut across the horizon, then you come back. Okay, that diagram has been mutilated. Let's consider for simplicity phi cubed. So remember what I'm doing? I'm just taking phi cube theory, putting it outside a black hole and asking what happens. Yeah, let's do massless for a minute. Now, if you want to compute, say, the generating functional for these correlators on the boundary, what would you do? You just put sources on the boundary. So let's say you put a general source JR on this side and the general source JL, and you'd use GKPW from the bulk and then write down the generating functional in terms of these sources JR and JL. Okay, so that generating function just comes from the on-shell action here. So the bulk computation is very, very easy. So if you didn't get the bulk computation, all you need to do is to take this theory in the bulk, solve the Klein-Gordon equation, put it back. Okay, Klein-Gordon equation with the phi cube source, put it back, and then find the effect on-shell action. That on-shell action will obviously depend on JR and JL because those are the boundary values of the field, and you're solving the Klein-Gordon with that boundary value. Okay, so let me quickly show you what the computation is, and then I'll get to the answer. Without telling you too much about the computation. So this phi you can expand in a perturbative expansion with this lambda, let me call it lambda 3 as the perturbation parameter. Okay, if you do this perturbation for the field, the action will also have a perturbation. So it will have a 0th order term and then a lambda 3. This will be a cubic coupling and then so on. So if you want to get the S3 for example is just equal to minus lambda 3 by 3 factorial square root minus 3 by 0. Okay. Okay, but notice that this integral has to go on the full GRSK. Okay, so these are all integrals on the full GRSK contour, which I'll denote by a no int. Okay. Now what do you have to do? You have to find this phi 0, which is some solution with this Klein-Gordon equation, which you can write down, and then you put it back in there and do the monodromy integral along this branch cut. Okay, and you'll get some answer. Similarly, you can go for, so this will be like a, let me draw this diagram. So on this GRSK, this what I just wrote down is a 3-point diagram. Going and interacting somewhere in the bulk. So the point is that basically you can draw Witten diagrams on the GRSK contour, and you can do all kinds of Witten diagrams. You can draw, for example, this exchange contribution, where you do this. Okay, so we know how to set up kind of a field theory. We know the vertices, we know the propagators, because effectively you just have to work with this and do curved space QFT on this geometry. Okay. It will be this versus
So if you have taken them on both, or do they correspond to different physical objects?
they correspond to different physical objects.
Different Feynman diagrams?
There'll be different diagrams, yeah.
So is it like?
But I'll give you a prescription to compute all of the diagrams. which is why I'm being slightly agnostic about the observable, because I want to just compute all the correlators and then worry about, okay, now how do I measure this?
Right now, you're not telling us that if I send in two particles.
No, that's not clear. That's not clear. Yeah. Okay. So now I don't want to tell you about all of the mess in this calculation, because you have to get a bulk to bulk propagator. That bulk to bulk propagator will have some theta function, some non-analyticity. So there are all kinds of non-analyticities with the logarithmic branch cut, as well as these theta functions, which you have to integrate along this monodromic contour. It's a mess, but after all the dust settles, we get a very clean answer, and we get exactly what you expect, which is an EFT. Okay, so now basically I'll not bore you with the calculation of how you get this EFT. I'll tell you what this EFT is, and that in itself will be interesting. First of all, I have to give you the propagators, and the result from here is that there are two different boundary to bulk propagators. These arrows will make sense in a minute. And I will explain to you what all these symbols mean. Okay. Unlike usual Feynman diagrammatics, where you don't put a source on the external lines, I'm putting the source in explicitly on the external line, so that's why you see the J is there, and the F and the P I'll make clear in a minute. So the question is, how do you compute these? This is just the ingoing solution, Klein-Gordon. So basically that means you do grad A on this geometry, and G in equals 0. Okay, and with the boundary conditions are such that G in are, this is some cutoff boundary. I mean, I can write infinity, but let me write cutoff boundary is 1, and okay. So basically you take the ingoing solution, normalize it to 1 at the boundary, and notice that I'm using radial coordinate explicitly, but going to Fourier transform space on all the boundary coordinates, convenient, because you have translation variance on all the boundary coordinates b comma x. So I just go to k there, and radius you can't do anything because you don't have translation variance, so you keep it as it is. So you just take the Klein-Gordon equation, solve it with the ingoing boundary conditions, that gives you an ingoing propagator. I will call this an ingoing propagator. Yeah, so at the moment there is no GRSK, all that stuff. Just take plain and simple ADSD plus 1 black brain, solve the Klein-Gordon equation, you will get an ingoing propagator. That's okay. Interesting thing is the Bose-Einstein factor here. It's just the usual Bose-Einstein factor. Maybe we should not write it. Okay. Note we are doing scalars, so it's not surprising that a Bose-Einstein factor shows up. These I will define in a minute, but I told you that you should put JR here and JL here. So there should be two sources. These are those two sources, but in a different basis, which is convenient. And G out is just the time reversal of G in. You can write down an explicit expression of this in terms of G in with the time reversal involution of the geometry. Okay, this JF and JP are just linear combinations of JR and JL. Let me write it down for completeness. F and P for future and past, because this is a causal set of diagrammatics. So the arrows, if you want, you can read already as causal arrows. So a diagram in which there is no arrow flowing will not contribute because the arrow is a time arrow. Yeah, so the K is right. Okay, so those are all the boundary to bulk propagators. You see that there is already an ingoing mode as well as an outgoing. Okay. Okay, good. Now the question is, how do you go from the bulk to the bulk? You need a bulk to bulk propagator, and there is only one bulk to bulk propagator because you're doing a causal thing. The K goes in. Okay, all my conventions have to be given, so this K comes down from the boundary to the bulk. Right to left, this minus I. Retarded propagator. Okay, forgot to say, usual quantum field theory, you would have thought that this should just be minus IG minus IG. It is. There is a minus I here, but then sources always come with an I, so the minus I. It's all very, very standard, except for that 1 plus NB, which is the thermal thing. So this is just the retarded propagator. Okay, which is a solution to radiate. Okay, I mess this minus sign up all the time, so that's maybe probably minus sign there times delta. Okay, you're doing this in momentous phase, so there's only one K. What happened to what in the? Yeah, so if you're doing just thermal QFT, let's say forget about black hole gravity, everything. You just want to take this room into thermal QFT here. The propagators will just be usual time ordered, anti-time ordered, basically Feynman, Dyson, like two different Weightmans. So you get those propagators here, and the vertices will be thermal vertices. Here, the vertices you will still, okay, let me give you the vertex story in a minute. I don't have a, I mean, if you're asking for why this looks like this, I don't have a very good answer. It just is so. But one reason could be that you could just absorb it into the JF. It's just a definition of the source. What going to zero? Zero temperature limit. Okay. Yeah, the zero temperature limit is not something I've thought about. Let's think about this. Okay. Yeah, RC is just the boundary. So it's just the cutoff boundary. So instead of going from RH to infinity, I'm just going from RH to RC because there are the usual ADS divergences and I have to holographically renormalize. So I'm keeping an RC. Okay. Okay, so those are all the propagators. Let me give you the vertices. Which Yeah. Exactly. Okay, now the vertices, and with this I will fully specify the EFT. There are two kinds of vertices, and this, notice, is a usual thermal field theory thing. You take a thermal field theory textbook and open it in this basis, you will see exactly this. This is equal to, if it was just usual no thermal nothing, it will just be minus I lambda 3. Let me do this for phi cubed. In the paper we have the answer for phi to the n. But then, since there is a temperature, there is a thermal field theory answer that this is equal to minus 50 ohms. Take it one the side, right? Let me check. No. Okay, and one more vertex. Okay, and this, if you can compare with a thermal field theory textbook, or even a thermal field theory section from, say Galis or something, these are exactly thermal field theory. So that's one of the punchlines of this work, which is that after all this dust settles, GRSK, whatever, blah, you forget all that, you eventually get, the expectation that, there is a black hole. It is basically hot. It's like a hot metal ball. What else will you expect outside? It's just a thermal field theory on the outside. Okay, with the temperature equal to the temperature of the black hole. Furthermore, the question is, of course, of what do you do at the horizon? What are the propagators? That question is answered here, which is that you have ingoing propagators, which take you, which is the dissipation mode, and then there are outgoing propagators for the Hawking radiation from the. Okay, so that's really the punchline of the work, and I'm kind of exhausted the story I want to tell you. We have, in this work with Shivam, we have generalized this to Yukawa theories, or more general fermionic theories, and you get exactly, Fermi-Dirac factors where you expect Fermi-Dirac factors. So it's kind of really magical once all the signs work and they give Fermi-Dirac factors. Notice also that you got a retarded propagator out of this calculation. There is no reason a priori with the GRSK space-time to have thought that, okay, after all these monodromy integrals you'll get some causal retarded advanced things, but you do. So GRSK respects, causality. Unitarity we have checked. It also respects thermality. All the vertices we write down are thermal. You can find out the correlators at an arbitrary correlator and check that arbitrary correlator satisfies KMS kind of thermality conditions. So yeah, and let me give you, what are you going to ask? Okay, unitarity in the Schwinger-Keldysh language is just this. So ZSK is just, you do the path integral forward and backward with the JR source and the JL source. Unitarity is just this.
I would have thought that you have to check something like optical theorem, and you can't do that with analysis.
But the optical theorem is inside this statement, is what I understand.
Usually we define unitarity on the.
Yeah. For me, what I mean by unitarity is this. Huh? These are just the sources. Okay, maybe one here. So this is, let's say you put a source JR on this path integral contour and a JL on this path. thinking. I'm trying to. You see, this is what we call something called as the Schwinger-Keldysh collapse condition, the escape collapse condition. And okay, this is not a computation I've done in recent times. So what you see is that constraints of unitarity on the path integral are equivalent to this constraint. This is something that I've seen in a calculation. I don't have an answer to give you. I'm so sorry. Yeah.
We check unitarity on the S3, not on the correlation.
Yeah, that's true. But maybe this is weaker than that. I don't know. Yeah, I'm sorry, I don't have a very good answer for it.
G's that appear in your calculation, that depends on RC.
Depends on RC in the sense that you want to, I mean, if you take RC to infinity, everything blows out. You don't want to do that, so you put an RC and then holographically renormalize at the end. But other than that,
When theta goes to infinity, then your NB is equal to 0, so you have only one of the J. You have only one kind of propagator, but is that the quick or?
Sorry, NB goes to.
NB is equal to 0.
Right. Yeah. And this is 1.
Goes to 0, so that is the guy that's the right, the other guy goes to 0 because your J goes to 0.
No. Don't do this limit on this basis. This basis is well defined only at a finite beta. In the case that you are talking about, you would have to work in the JR and JL basis and then do the limit. Don't do the limit on this.
There will be some step function, maybe take step function that will come out from the
From what limits?
I mean, if I, so what these
You'll get two propagators, right? You'll get Feynman and Dyson. Yeah. So with these rules, you can now sit down and compute an arbitrary diagram. For example, you can draw this Witten diagram. This is one of the many 4-point functions. And with these rules, you can write it down explicitly. You can show that this goes as, yeah, I mean, this goes as something you can write it down explicitly. To summarize, we have an exterior field theory computes. Okay, I forgot to mention a very important caveat, which is that notice that I did only phi cubed theory. You can go to an arbitrary phi n and you can generalize these Bose-Einstein factors. There's a very neat generalization, and almost everything works for phi n. Actually, everything works for phi n. But when you have derivative interactions, this picture of an EFT is not true. Okay? So the standard model has derivative interaction. So if you have a derivative interaction, QED everything will work, is what we think, because we have shown it for fermions as well. But if you have a derivative interaction, what happens is that the horizon becomes special. So over and above this EFT, which is in the exterior, there are terms which are localized only on the horizon. Okay? We don't understand it any further than what I just said. There are terms localized to the horizon, so which computes an arbitrary. I'm saying a very simple thing, which is that if you compute this 4-point correlator on the boundary, I'm saying that for these theories at least, you just put vertices in the exterior and you integrate it from RH to RC, integrate it over this space. But if you have a derivative interaction, let's say del mu chi to the n, what happens is that over and above this diagram and integrating till here, there are terms purely localized here. There's a delta of R minus RH something, which we don't understand. Okay. And we are at the moment trying to Okay, this also works for fermionic theories. So in fermionic theories, what happens is that if you have two bosons coming at a vertex, it becomes, sorry, two fermions coming at a vertex, it looks like a boson, and you get a Bose-Einstein factor. The fermions get the Dirac factor, the F and the B. All that very neatly happens, and you get exactly thermal field theory even for that, which most people don't write down somehow. It was very difficult to find those vertices in a textbook. At the moment, though, we're kind of generalizing this to loops. So these are open questions. How do this? Or do these results work for bulk loops? And this is something we're doing at the moment, and it seems like it works. Basically, what I'm asking is, I've written down an exterior field theory. Can you also draw bulk loop diagrams for this exterior field theory and understand purely bulk mass renormalization question, for example? This is something we're doing at the moment. We're writing down the Schwinger-Dyson equations to lift it to the full quantum field theory. Yeah, this is still work in progress.
Is it surprising that you have these localized modes? So if you're doing the calculation for black grain, so in string theory, if we had a single grain, so sort of a single grain, those string comes and it becomes open string, which will be on the grain.
Yeah.
You will have these degrees of freedom that are localized on the string.
Yeah. Yeah, possibly. But somehow I feel like this will survive even for a black hole.
Yeah, black holes, if you think of it as a bunch of brains,
okay. Yeah, possibly. I don't know.
Yeah, so the scattering process in the string picture would be a closed string coming in, becoming two open strings, and the two open strings joining back and forming a closed string which goes back into the bus. That's the string picture for. No, I mean, a closed string could be a Dylan
Yeah, so maybe I should say just one quick word about what happens here. So remember that I drew like a GRSK contour that looked like this. And for this exterior field theory to work, you basically should not have a divergence here. The branch point should not also be a pole. But in derivative theories, that happens. The branch point becomes special because it's also a pole, and then picks up purely horizon localized contributions. So that's what happens for derivative theories. You don't really understand it any further than what I just said. Yeah. One final comment is that I didn't mention the CFT anywhere in this whole talk, but if you're an ADA CFT person interested in CFT, this computation that we have done of finding the Schwinger-Keldysh correlators of the CFT is equivalent to finding an open theory for a probe coupling to a CFT. Say n equals 4 pseudo. In general, there is. This calculation is equivalent to, you take a probe, you take just a quantum field theory, you put it in contact with the CFT, the boundary CFT, and then you integrate out the CFT. And then you ask what is the open theory for that probe. Okay, so this is this not in our work, but the one preceding this was the first derivation of an open quantum field theory this way, because open quantum field theories are very hard to engineer, because as soon as you start integrating some fields out, things will become non-local and things go haywire. So engineering open quantum field theories itself is a very difficult question to answer, and this is a holographic derivation of an open quantum field theory. So maybe I should continue. And this open quantum field theory has its own fluctuation dissipation theorems and everything which come from this bulk picture. Yeah, I mean, that also has an interesting story there. Which retarded correlator? Uh-huh. Oh, no. I think you're talking about the. Are you talking about the retarded correlator in the CFT? That's just the the boundary limit of this. The ingoing boundary to bulk propagator, if you take a boundary limit, it becomes the retarded two-point correlator of the boundary. No. This is all bulk calculation. Oh, you're asking, can you do it in the CFT? Yeah. I don't know how to do it in the CFT. Yeah, I don't know what bulk scattering of I cubed particles looks like in the CFT. I don't have a very good answer. Yeah. Yeah. Temperature beta, yeah. No, it's just a black hole at a temperature beta, right? I'm not changing the temperature. There is no non-equilibrium thing happening. This is like close to equilibrium, at equilibrium. Yeah. So I am computing only the boundary correlator. So this is some bulk effective field theory or a bulk field theory to compute these boundary correlators. So I'm computing only boundary correlators. So if you remember this. Because you're computing Schuhy-Keldysh correlators on the boundary, not time order correlators on the boundary. Yeah, retarded one you can get from here. So this, for example, like you could have forgotten about everything. This people computed like long time. This is very easy to compute because you just put ingoing boundary conditions on the horizon. You just say everything goes away. You get a retarded propagator at the boundary. Yeah, that's true. But the new question, which probably missed, is that you have a black hole and the stuff going in, of course, which is just the ingoing propagator, but then stuff can come out, like a photon can scatter against this electron and do whatever. So the question is, how do you understand this physics? And for that, you get these outgoing propagators as well. The story. Yeah, this I think Karen Horton and others have done a good job. Okay, this paper I've not like completely read to the delta, but I think this will be very useful. But that came out after we some OTOC gen. Yes. Yeah. So the question is, what these people compute, is it principled in the sense that it is field definition? I hope it is. You're saying they're doing a purely particle thing and they get like they know field, so everything fielded. Yeah, but the unitarity question, I'll get back to you. I'm sure there's a very clean answer to it. Yeah. One thing that I did not talk about that maybe I should have mentioned is that the physical question you have in mind, this after all this technical stuff goes away, the physical question we have in mind is the following. Which is what at least I think will be the first time we see Hawking radiation from a black hole. If you have a black hole there, and this question I asked is, oh, you throw an electron in, what happens? But then that's not a very physical question to ask, because you throw an electron in, say 5 photons came out, but those 5 photons could just be the hot metal ball radiating, right? Because that just could be the Hawking radiation. So really, to make this a very experimentally well-defined question, you want to throw a huge shower of particles into the black hole. So how do you engineer that? A star. So you put a star behind a black hole, you put a black hole there, and then you stand here. Classically, we know what the answer to this question is, because the star's light gets lensed, you see an Einstein ring. But then now the question is, the black hole is fuzzy because it's Hawking radiating. how does this Einstein ring change? What is the mean position of the Einstein ring? What is the standard deviation, etc.? What are the properties of this Einstein ring that are dependent on the Hawking radiation? So that I think is the physical question that we're trying to answer at the end of the day. So the question is, after all this LSE stuff, can you get like what happens to the image of the Einstein ring? Yeah, 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 exactly. You mean the recent chemos paper, like December paper? Not with a black hole. Oh, no, I don't think, I don't know, I don't. Deflection angle with Hawking radiation, no. Yeah, without Hawking radiation, classically, yeah, that's what KMOC people do. In fact, KMOC also, not KMOC, but the OC from the KMOC, O'Connell, this December, just a month ago, wrote a paper called Amplitudes for Hawking Radiations, where they're basically doing a semi-classical calculation to get, how does the Hawking radiation affect these scattering processes outside, and they basically use Karen-Huat's techniques to get these amplitudes. We want to make connection to that work, including these effects, and basically question is, can you do this to get that? Yeah, that's an interesting avenue which we haven't touched yet. Recently saw the paper. I'm going to remove this, is giving me a headache. Very, very interesting. You basically have to do this calculation on the CFT. Instead of computing a time-out correlator, you have to compute this clinical correlator on the boundary, and that, okay, if you compute that independently, should match this with this. Yeah. Yeah, no fights. I'm just saying, take the CFT, put it on this contour. On the CFT. Yeah, usually when people say OTOC, they mean a more general thing than maybe what we tell. So all correlators, including all micro correlators at any point, can be classified, can be graded in the following way. You can start with time ordered, and then you say, oh well, I can do time ordered, anti-time ordered, so that I have one notation. Most people conclude something like this. This has been computed in a again. Okay. Is it a sensible question to ask? Can you rewrite this in, like, can you get this structure out of this? Writing this?
There was a bulk
Very good.
that using my
Yeah. Okay. People trying to sort of this by just doing the Euclidean computation and trying to see how much you can pull the Euclidean computation, pull it up if you reach a singularity, and show that basically. What is it? But what real time is something I should have prepared for. Real time is something I should have prepared for.
What is the derivative thing? You were saying that you're getting some full life singularity for derivative in that. Why are you worried about that?
So remember that okay, assuming that you have some belief in the GRSK, you just want to do this integral. The statement I was making is that, oh, you do this integral, this circle doesn't contribute, so that's just 2 copies. So it's just 2 times this line. So that's just 2 times exterior field theory. That's the exterior field theory I got. But then, if there is a pole here, it's the exterior field theory plus this, plus something happening at the horizon. I mean, it's a funny statement to say that derivative interactions somehow know about the horizon, but that's what we see.
Some of the times the finite thing with your derivative that you so you have a derivative interaction that will add to more powers of base like
Oh, okay.
when you go to finance. Yeah, I think because when you have derivative interactions, you'll be forced to work with the cutoff. Or that is transferred some position cutoff as well. So maybe you're not allowed to extend
All the way till the horizon.
the other way. But they're not doing a high energy. This can be very low energy. They're not producing a lamp. Studied they also doing freedom. They can study in some air. I think it's all in the air. Yeah, but it has then theory also knows about the maybe you need to add then if you demand consistency with UV unidirectional. I mean, the observation is that there have a time cutoff. The time of the scattering, space time, has to be smaller than the black hole evaporation. If they wait for long enough for the black hole to evaporate, then it's a difference. Right? Yeah, but these are all cutoffs. So the observation is that like finally the AFT is just a equilibrium harnessing. Yeah. Then if you want to do it from a direct safety calculation, why do you arrange the safety side from the safety side? Why do you need CRS?
You don't. I mean, if you're just sitting in the, yeah, if you could do the calculation of the safety, amazing, yeah. But yeah, we don't know how to do it, or at least okay. No.
Different from what you are asking in the safety side. This software, they are not the same thing.
Maybe.
I mean, you see that the safety you are getting from this part set about GRS camera. That's finally the boundary safety is a equilibrium.
Yeah. So it's just thermal circle on the boundary.
Yeah.
And then I want to compute this path integral with the thermal circle. That's all it is. So you have a thermal state. Compute for me a real time 4-point correlator in the thermal state. I don't think that question is easy to answer. Because usually you would say, oh well, forget this, do a Euclidean computation, then analytically continue. You see the Bose-Einstein factors here. Right? Analytically continuing and increasing Bose-Einstein factors is a madness because each Bose-Einstein factor is a master sum there. You have like products and ratios of Bose-Einstein factors, so it's just gory mess. So that's it. I mean, in principle you can do it. In principle you can do QCD with canonical coordinates. That's it.
Because the generalized attitude, so the calculation they were saying, so they have some wave functions and they're taking expectation value of some operators with the wave function. In your picture, is the notion of that wave function defined? Meaning, so they are starting from the back move and corresponding to those back move, like when So here the wave function.
That whole picture is not developed yet. Would be nice to get that. Thank you so much.